Welcome to Module 2. In this module, we're going to discuss vectors and the multiple forms that we can find a vector kind of in. We're going to also talk about a Cartesian coordinate system and a little bit of the basics about the theory of vectors. And then we're going to go inside of Houdini and start to look at how to create and manipulate vectors, how to visualize the vectors, and also some kind of little nuances of handling vectors and vector types inside of Houdini. And then after that, we're going to wrap up the module by looking at some examples and how we can create some practical kind of setups and workflows with vectors. Okay, so I'm sure everybody is familiar with kind of what a vector is and they've kind of come across them in the past. I just want to talk about the different types of vectors and how the phrase or the term vector can be used. Now the first is the kind of position data that you might get, what we've kind of worked with in the previous module with the sine and cosine. We've been manipulating the position data of a point, and that's just represented a magnitude or a scalar value, and that's typically how a position is kind of represented in that straightforward manner within Houdini and other 3D packages. And then we're going to move on to vector, the geometric sense of the word vector. And that's really kind of what this module is about. And it's the idea where the same value, so as you can see, the kind of example, which is open bracket 10, 12, 5, close bracket, that's essentially the same as you get with a scalar, but it's going to be used in a different way, and it's going to conceptually represent different types of information. And that is direction plus magnitude. So it's not just an offset, it also has a start and end position. And then there's the vector data type itself. Now, the vector data type is just essentially a vessel of holding more than one numeric value at a time. So it can be vector 2 type, or a vector 3, or vector 4, and it's just basically a container that we can use to either, have our scalar values like we would with the position attribute in Houdini, or it will have the vector information like you would get with velocity attribute within Houdini or other such packages. So they're the three kind of conceptual ideas that are all represented in the same way numerically, but they and the phrase can be used in a very similar way. But that's just mainly kind of the terminology and the context that it's used in, which really gives it its meaning or its distinction. So I just wanted to talk about that briefly, and we'll go on now to talk about the Cartesian coordinate system. Okay, so we both have two examples of the Cartesian coordinate system, and this system is something that everyone, I'm sure, is familiar with. It's basically the way of describing a position in three-dimensional space. It's the straightforward kind of X, Y, and Z for the up, side, and kind of back directionality of positioning something within Houdini. On the left-hand side, we've got a two-dimensional Cartesian system, and as you can see there, we have, if you look at each of those points, you have a vector, two-dimensional vector, which represents the position of those points on that two-dimensional plane. Now, that's just being represented as magnitude, so it's just the magnitude of how far along X and Y to describe that location. And if we look on the right-hand side, that's the exact same thing being done, but in 3 dimensions. Now, this is how the same vector kind of numeric list is representing magnitude or a scalar value, such as position in Houdini. And that's a big distinction, because that's how that's conceptually being used, even though the actual value, the attribute, will have the same kind of three float or 2 float value that you will see with actual vector, a geometric vector, which we're going to show on the next slide. Okay, so now we're here and we're looking at our vectors, our geometric vectors. On the left-hand side, we have a 2D version, and as you can see, we've got A and B here, which are how it's being represented on this graph, which would otherwise be X and Z. x and y, sorry. And we have this point here, this position, and that represents the actual sort of head of the vector, and then the base of it is the origin down here. So as you can see, you only really need to describe where the head of it is. That's why we can just have this simple two-dimensional vector here, which could also be used for position data, but if we conceptually use it as a geometric vector, it's going to automatically use the origin as the base, and then it's going to create this kind of imaginary line that runs up to the head, and that's what gives it its directionality. And then the distance to the tip or the head of the vector is what gives it its magnitude. So that's how we have these two different pieces of information being represented with the exact same vector data type that you would get with position or something similar. Again, in our 3D vector over here, we have just obviously the addition of z, but you can see it works in exactly the same way. We have the base over here being at the origin, and then the actual values that we have to describe our vector is what's describing the tip or the head of the vector. And then that's how we know our directionality, and the distance between these 2 points is how we know our magnitude. Now this is obviously fundamentally different from how we perceive it from position data, which position data has no kind of relation to the origin in the same way that this does. It's just literally an offset, and then it's a single point in space, whereas the vector has a start and an end. And we don't really need to describe the start of it because we describe the end, and the start is automatically assumed to be the origin. But then when we add it to other vectors, then it gives us a relative offset in 3D space. And this is what we can use to create really cool animation and deformations. It's a really powerful concept. So we're just going to have a quick look at the way we can add these vectors together. So on the left-hand side, we have 3 vectors. We have A here, sorry, B here, and A here. And as you can see, these vectors are relative to the origin. And then when we add A and B together, we're getting this red vector, this new vector here. And what that's actually doing is, if we have a look on the right-hand side, we've got the first leg, so we've got the A vector being added, which runs up here, takes us to this location, and then we have the B vector added, which then offsets our point up to the final resting position of our new location or new vector. So we can see this is how it's given us a new vector, but it's also, you can see that the different steps involved here. But we've got basically a description of a path that it's followed. Now if this was to be frame 0, frame 1, and then frame 2, as we add these vectors over time, then we can see how we can describe motion. And that's the fundamental idea of how basically every kind of, piece of geometrical animation takes place in most 3D packages. It's really a workhorse of visual effects and something that's used again and again. And it's a simple idea that we can really create some quite fascinating and kind of captivating particle simulations and deformations and things like that. And subtraction happens in the exact same way. When it comes to multiplication, it's when things get a little bit more complicated. We're going to look at ways to multiply them in kind of to create interesting results in Module 2. But when it comes to just a simple multiplication of a vector by a scalar, so multiplying a vector type by a single value, that's when we can just scale it. So we don't change the directionality of our vector, but we change the magnitude. So if we were to take, for example, if we were going to go over here to this A vector, and we're just going to multiply it by a factor of 2, it would just scale the same direction until it was twice as long. It wouldn't change the directionality at all. It just changed the magnitude of it. which is a great way we can scale up different effects quite easily inside Houdini. So that's a quick look at some of the basics and the different definitions of vector and vector types. Let's jump into Houdini and get started on how to use them and how they can be manipulated.